standard derivatives and a single different table of standard integrals so that you don't look at the wrong table, right? So you know, oh, I'm differentiating this, it belongs from this table. I'm integrating that, it belongs from another table.
Yeah,
because you do both of those very often, right? Questions expect both of those things. So any kind of notes that you would feel that would be helpful, any kind of standard integral tables, unit circle stuff, any trig identities that you're a bit dodgy on, that you think, oh, I better remember that trig identity. I mean, if you can physically write it down, you'll be able to use it. Okay. That's it. Any more questions before we actually officially started on this last chapter, this last section?
Is 3 hours going to be long enough?
Should be.
Well, because you said that about one of the tests, and
yeah. Well, as I do, yeah.
Holy moly!
What happens? Sometimes you can do a question the long way and there's a short way, and so it does take you longer because of that. Normally, I just look at WebAssign and it tells me how many minutes the average student took to do a particular question. And so if I'm doing a 3-hour exam, which I will be, I'd be looking at that and saying, okay, I'll make sure the typical student did it in 2.5 hours, and then the little half hours wiggle room, and that should be it. Evidently, in one of the tests, you were saying it took longer than that.
Yeah, it took me. Well, I had to guess like 3 problems because I wasn't even
Run out of time. Yeah. You know, I don't want it to harm. I guess it could harm. I'll plan for it not to harm. But you know, if you spend too long on a question, that kind of eats into the other questions. So that's something to be aware of. I'm looking. I haven't written the thing. I don't like doing that until after the class is finished. That way, I can talk about it and I don't feel that I'm giving clues away or false ideas. My gut feeling is that there's probably going to be more than 10 and less than 15. So that's how many questions. And the questions will be different values. I mean, if it's a big, horrible, long question, you're going to get more points than if it's a little quick one. You know, if I went and said to you, here's R of t, what's the velocity, acceleration, and speed? You know, one of those questions. That's pretty straightforward and pretty quick. On the other hand, if I gave you, here's the acceleration, and R of 0 is this, and V of 0 is that, and I ask you to work backwards, that takes more work, and therefore you should get more points. So it won't be every question's worth the same. What else? I'll make it so that you can have as many shots as you like, but since it won't tell you if you got it right or wrong, there shouldn't be a problem with that. Once you're comfortable with it, since I'm going to be seeing the working, in a lot of ways, the midterm on WebAssign is just a placeholder for your answers. You know, if I can see you're working and I can see the answer and I know it's right, then it's pretty easy to grade. And if it's not right, then I have to spend the time going through it to see, was it a minor mistake or was it something more major? Any others questions?
So everything, for instance, that's covered today and Monday will also be on the test.
Everything up to today. Monday is not going to be a class day. Monday is just going to be devoted to nothing but your midterm. Okay. So I might be here for a couple of hours or whatever, just because you might want to do it during the time I'm here, because then it's easy to communicate with me saying, hey, question 8 don't make sense, or should that have been a square root, because whatever, you know, I can't photocopy it. What's going on? What should I do? So I'll be kind of hanging about for those kind of reasons, but not really, not to teach a lesson or anything. I'll just be here.
Thanks for the answer, but I meant this past Monday.
That video is part of, is part of today. So is today. So the last thing your topic's going to be on is 14.3, what we're doing right now. Right, so the first thing will be week 1, And the last thing we'll be covering is 14.3. I almost always do my test chronologically. So the first question's from week 1 and the last question will be on partial derivatives. Are we good? If you think any others, you can do it at the end. Right, so I believe, please tell me we have, because I've got 2 classes and I know I've done it with the other one. I believe we just started partial derivatives. Is that correct? Did we talk about them?
I don't recall.
Right, so that means we just finished on the last stuff and that's fine, which was limits. So let's start with partial derivatives. Multivariate function. If I gave you a function like 3x squared plus 7x, and I ask you to differentiate it, this is Calc 1, you'd use the power rule, right? We're all comfortable with that. This is a single variable function. And the variable is clearly x. And the rules of differentiation apply. Now, when you differentiate things, the typical rules that you're going to use are the first rule you would use would be your power rule, which is what I'm using here. The second thing are standard derivatives. Right, the standard derivatives are those guys we just memorize, we memorize the answer to. Right, if I say to you, what's the derivative of e to the x, you just say it's e to the x, right? Because you know it. If I say to you, what's the derivative of sine x, you would say it was cosine x, right? If I ask you for the derivative of secant x, you would tell me it was secant tan, right? Those are called standard derivatives, right? There's no way to get the answer, you just remember the answer, right? There are standard things we know the answers to. And so that would be for things like differentiating, I know, secant x or log x or something, right? And then we move on. So we're really doing Calc 1 here.
You know, I really want to know why you guys think secant x is standard, because it's not on any of the calculators.
Blame well, you do know it. It's 1 over cosine x, right? So it is, you are able to type it in, right?
Yeah, but come on.
It's not that standard, I guess. It's one of the 6 trig ratios, so it counts as standard. That's the best I can say for it. Right, the third thing is that you sometimes will use what's called the product rule. And that would be if you were wanting to do a differentiation of, say, 2 things. Like that would be a product rule question. Sometimes you differentiate things and you'll need to use what's called the quotient rule. And the quotient rule would be if you wanted to differentiate a fraction, right? And then essentially the last major rule that you use is called the chain rule. And if you want to differentiate that, you would use it for things where you had like a function like e to the power of sine x, or if you wanted to do the square root of x squared plus 2x, things that look like that. These would be chain rules, right? So these rules still apply on this new guy that we're going to learn about called partial derivatives. But we first learned all these rules when we were doing functions typically of a single variable x. So what we're now going to do is we're going to extend the idea of differentiation to multivariable functions. So your function is not going to be called f of x anymore. It's going to be called f of xy. It might be that's a very simple one. You will sometimes see it written down as z equals 3x squared plus y cubed. That is an example of a multivariable. This is a two variable. Z is equal to 3x squared plus y cubed. X can take any value it likes. Y can take any value it likes. If you plug those kind of guys into GeoBra, don't you end up with those nice weird surfaces that look like the tops of hills, or the fancier ones with the cosines? Didn't it look like ripples of waves going outwards, right? We can differentiate these functions. The major issue is, and these functions are multivariable. Oops, I guess E. No, you won't have E. Multivariable functions. Now we're going to find a technique for differentiating them. The big problem is there's two, maybe 3 or 5 or 25 variables. There's typically two, right? Two variables. This is the notation for what's called a partial derivative. You can differentiate this function with respect to x, and when you do that, we call this a partial derivative of z with respect to x. Now, that partial derivative is sometimes written as z with a little x. That partial derivative is also sometimes df by dx, and that guy is sometimes called f little x. They are all the same thing. They are just different notation for the partial derivative of this multivariable function with respect to x. Now, the way you find the partial derivative involves us making, I don't know if it was a decision. When you look at the function, you decide x is a variable. And the minute you make the decision that x is a variable, right, all other letters of the alphabet are treated as if they were constants. They are treated as if they were numbers. So I'm not thinking this as 3x squared plus y cubed anymore. I'm going to think of it as 3x squared plus 42 cubed, right? Just a number cubed. So when you find its derivative, you differentiate this guy with respect to x, and it's the same rules as it's always been. But what do you get if you differentiate a number cubed? Or anything that's a number? What's the derivative?
0.
0. So that's our answer. Just 6x. You don't say 6x plus 0, right? You just say 6x. Now, if I asked you, I'll write that one down here. If I now asked you to do this guy, which is the partial derivative of z with respect to y, then you go back here and you say, okay, y is the variable. So I'm going to differentiate that guy, right? And this guy here is going to be treated as a constant. So this will be 0 plus 3y squared. And so the answer is 3y squared. So far, so good. So the trick to doing what's called partial derivatives is to realize that you consider only one letter as a variable, and all the other guys, you treat them like numbers. You treat them as constants. And if you can keep that process in your head, because it's a bit like, well, sometimes it's this is a variable, and then sometimes that's a variable. You see how you keep changing who you consider the variable depends on the question. X
So
is a variable,
if you had,
y is a variable.
if you had z is equal to 3x y squared x squared plus y cubed, and you wanted to differentiate in respect to x, how do you treat the y in that term?
Let's do it. So let's say, it might not be exactly what you said, but it's the gist of what you said. Suppose we had that, right?
Yeah,
Right,
that.
3x squared, right? And let's put in, just for general interest, let's put that in. And I'll even put a y squared in, right? So a little bit of everything. Now, if I want to get the partial derivative with respect to x, I need my little piece of paper. I can use this, right? just want to hide them so they're just not distracting us. X is a variable. Y cubed is considered a constant. So do you know how that says 3x squared? That y cubed is just the same as that 3, right? It has the same properties. So when I differentiate this guy, won't I multiply by the power and reduce it by 1? Can you see that the only guy that changed was the x squared generated a 2x, but everything else is still there? Does that make sense? A bit like differentiating 3x squared, what would you get? Well, 3x squared y cubed is pretty much the same thing, isn't it, as 3x squared? You just have a y cubed, like a times 5 tagged on at the end. Now, what would that guy get you if you differentiate with respect to x? What would this guy get us?
It's going to be both constants. They're going to stay there at 5y.
Right? And see
So
that
that
little
makes
y
total
squared?
sense to me now. Like,
Oh, good. Right. And won't this guy just be 0 with respect to x, right?
So just real quick, what happened to the x for the 5xy?
Right. Well, if I went and said to you, differentiate 5x, wouldn't the answer just become 5? Calc 1, right? Right. If I ask you to differentiate 5xy, the answer becomes 5y. And if I said differentiate 5xy cubed, the answer just becomes 5y cubed. You see the y or whatever else happens to be there, the other letter, is treated as a constant. So it's just like just like having a 5 there, right? It's just another number that happens to be using a letter of the alphabet instead of 5.
Okay. Yeah, that makes sense.
Now, let's do the same guy, but with a y. Right, now you look at this term, would you agree that's y cubed and the rest is basically a number? So multiply by the power becomes 9 and reduce the power by 1. So your 3 3s get you 9, and then you have that. Does that seem reasonable? 3 times the y squared. Now you do this guy with respect to y. Then very similar to up here, but do you notice it's now 5x that you get? Now this guy, because he is a y, you get, I guess, calc 1 way of doing it, right? It's just 2y. So you notice that this thing has 3 terms, but this one only has 2. Are we good? Just hold on a second. I'll pick something from the homework. Okay. This is an example or a version of question 2. The function uses x and t instead of x and y. That really isn't that significant. And it's t squared e to the negative x. Okay, that's the function. And we're being asked to find the partial derivative with respect to x. Okay, x is a variable here. Isn't that guy just 42? It's just a number. Treat him like a number. So if you differentiate this, won't you do multiply by the power, right thing, you know, e to the minus x? It's essentially, it's a chain rule. And so what do you get? You get negative t squared e to the negative x. Are you comfortable with that? Derivative of e to the negative x is e to the negative x times the negative 1. What about the t squared? The t squared is still there, right? Now, I want to do a different version of that question just to make sure that we're clear the effect of where the other letter is. Suppose I separated them out as a t squared plus an e to the negative x, right? It's not the same thing, right? This is multiplied, this is add. So if you were differentiating this partial derivative with respect to x, the answer is quite different. Won't that t squared disappear to 0? And won't this be the only thing you end up differentiating? And that would get you that. You see the difference? This is attached to that. this is kind of separate from that. Now they ask you for both versions, so just for practice, oops, that's a t. If you differ partial derivative of this with respect to t, aren't you going to get 2t e to the negative x? Are you comfortable with that, guy? If you differentiate this guy with respect to t, that's basically just a number. So 2t with that guy tagged on, right? It's a bit like 5x squared gets you 10x, right? I need feedback here. Good, bad, or average? Are we good?
I'm
I-
good.
I'm good. I have a quick question though.
Yes.
Are we ever going to come to a point where we would have, like, instead of 2 variables, we would have 3, like an x,
Yes.
y, and a z?
Yeah.
Okay.
Or 10. Don't really do many of them, but let's show you one. Suppose I have a function w of 3 variables, x, y, and z. Actually, why don't I just call it f of x, y, z, because I like f. And it's equal to x, y squared z plus zy plus x to the 4y, right? So it's just a mixture of x, y's, and z's. Agreed? That can happen. Now, if you had a function like that, this would be considered a 4th dimensional function and a 3 variable function. Why is it 4 dimensions? Do you know if you have 2 variables here and this guy here, if you sketch it, don't you get a 3-dimensional surface? Well, if there are 3 variables here plus the answer, that generates a 4th dimensional surface. Nobody that I know of, unless they're in a mental institution, can actually visualize 4th dimensional surfaces, right? So we can't rely on imagining what it would look like. Isn't it now just pure math? This is what it is. We'll find its derivative. So if I asked you to find the partial derivative with respect to x, you would take each one and you'd say, okay, x is the variable, everything else is just a number. So if I differentiated this guy, I would get y squared z. What would I get if I differentiated 7y with respect to x?
You'd still have zy.
Oh, would we? Isn't that just 42 times 50? Isn't that just a number? There's no x's involved.
Yeah.
So
So it'd be 0.
It'd be a 0. Now, this guy over here has an x in it, right? If you've got an x, then there's probably something going to come out of the derivative, right? In this case, wouldn't it be a power rule? And you'd have 4x cubed y. So that would be the first one. If you did a partial derivative with respect to y, right, middle term, it's a variable. These two either side of it are really just going to stay put, right? They're just constants. They're like 5y squared kind of thing. So I'm keeping that guy, I'm keeping that guy, and this guy gets derivative, and you get 2 of them. And so you get 2xyz. Are you comfortable about that one? Right. Now, what would happen to zy if you differentiate it with respect to y?
You'd just be left with a z.
Correct. And if you differentiated x to the 4y with respect to y, wouldn't you also just be left with an x to the 4? And the final one of this list is this one. And if you differentiate this term here with respect to z, isn't it a bit like having 5z just? So you differentiate it, you get xy squared. If you differentiate this guy with respect to z, you get y. And if you differentiate this guy at the end with respect to z, what will you get for this one? What's the derivative of this one with respect to z?
0.
Big 0. Have you noticed that these 3 partial derivatives are quite different from each other, at least reasonably different? That's not a coincidence. Would you agree that's probably what you'd expect in almost every situation? That when you differentiate something with respect to x, y, or z, it's quite reasonable to assume that the answers will be different in some way. Now, for those who want to get a feeling for what is a partial derivative actually calculating, right? What am I getting when I find a partial derivative at a particular point? So
You're
let's
getting a
go.
slope.
You're getting a slope. Yes.
Yeah.
Is that what you said, John? Yeah. So let's suppose I have, and I'm picking the simplest thing I can imagine, that guy, right? And the reason I'm picking that guy is because I know what he's going to look like. Isn't it that guy that looks a bit like a cup? Right, that's what that would look like. Right. If you prefer, I'll call him Z equals, which is equivalent. Now, when you do a partial derivative of Z, say with respect to X, right, what you're essentially doing is you're taking this shape, and there's X-axis, and there's the Y-axis. And you are slicing this shape parallel to the X-axis. So can you imagine that I cut it like a cake here, right? Like over here somewhere. If I cut that, can you imagine the shape I might get would be a single two-dimensional curve, right? And then if you were going to find that partial derivative, let's say at the point 1, 2, right? Then what you were really doing is you're trying to say, okay, what's this curve going to look like when X is 1 and Y is 2? And I don't know, let's say it's there. You are finding the slope of the curve formed by slicing that guy parallel to the X-axis. In this case, at X equals 1, right? Y equals 2. When you slice it at that point, you get a curve, and you get a point on the curve, and you're finding the slope of the slice parallel to the X-axis or the slope parallel to the Y-axis. I don't know if that helps or hinders, but that's what you're finding. Now, if I was telling you a different shape, suppose I had a shape that was, one of those double hill things. Some shapes look like that. If I was interested in finding the exact location of these two hills, I could use partial derivatives to do that. Would you agree that at the top of that hill, the slices both generate, if I cut it horizontally, wouldn't it be the top of a hill? And if I cut it at right angles, wouldn't it still be the top of a hill? Can you see that, guys, the top of a hill both ways? That means all I need to do is I only need to find out what value of X and Y are both those derivatives 0 at the same time. So we can actually use partial derivatives to find the local maximum and the local minimum on any of these 3D surfaces. You solve when is the first derivative 0 and with respect to X, and the first derivative is 0 with respect to Y, and the only places that's going to happen is here. Right? Does that make sense? So that, if you like, that's a reason or a motivation behind why we try and find these things. One of the things they're allowed to tell us is locations of interesting points. Now I'm going to start introducing more and more complicated things to find partial derivatives of. There are essentially 10 questions, the first 10, and essentially question 20 as well, where we're only finding first partial derivatives. They just get uglier. So how about this function? And this will test your ability to understand how to treat one guy as a variable and the other guy as a constant. So if I asked you to find the partial derivative with respect to X, there's the notation I'm using. When you look at this question, do you see two things that have X's in them? being multiplied together.
Mhm.
Do you see then that I'm going to have to do a product rule to find this guy's derivative, just like I would have done way back in Calc 1, right? Now, what's the difference? Well, there's a y there instead of sine 2x, right? That's the major difference. But it's not really mathematically that significant. So the product rule. Now, if you differentiate this guy with respect to x, you get 1, and you leave this guy alone. So it's 1 times the sine xy. Plus, you leave this guy alone, and you differentiate the sine of xy. And I'm now about to do a mistake. I know how to differentiate the sine of xy. It's the cosine of xy, which it is. Times what? That's my mistake. I didn't put in the times what. Now you've got to be careful. Isn't the inside function xy? Now, if that was 2x, wouldn't I do times 2? If that was 10x, wouldn't I do times 10? Well, it's yx. So what should go here?
Times y.
Times y. And then make it look pretty, which you can't really do that much to it, but that guy and that guy. So here, that was our first question, where we needed to use the product rule. And technically, isn't that a chain rule, this bit here? Right? Now,
Yeah, that's
partial
definitely going to take definitely going to take some time to get used to.
yes, it is. It is similar enough to Calc 1 to make you feel like you know what's going on, but different enough from Calc 1 that you have to be careful. Right, let's differentiate this guy with respect to y. Now, one of the strategies you can do, if it helps, I got that one right.
It's no longer a product rule though if we do that, right?
Correct. It's no longer a product rule.
There's a chain rule.
It's just a chain rule. And so what you're going to get is x, fine, the cosine of xy times the derivative of the inside function with respect to y, which gets me another x. So can you see how the answer didn't need a chain rule? Sorry, didn't need a product rule, it only needed the chain rule. You see the difference between this answer and that one? By the way, I should have called that guy up there 5y.
I'm a little confused why the x is on the outside if you're taking the differential of y.
Well, let me isolate it to just one thing. Let's suppose I said to you, differentiate just that. And I want, let's call that guy f. And I want you to differentiate that. Well, it doesn't matter which. Let's say with x. Then you should think of that as 5x. Like y is the number 5, right? I just picked 5 at random. Now, if I asked you to differentiate that, you would be saying, oh, chain rule. Cosine of 5x times the derivative of the inside function. There's my 5. Agreed? Now, that guy, that y, is essentially just like a 5, right? It's treated as a constant. So when you differentiate it, you should get the cosine of xy times the derivative of the inside function. And if you differentiate that with respect to x, don't you get the y? Can you see where the y is coming from?
Yeah.
Right. So when I do it with respect to x, you know, you get a times x, and well, when you do it with x, you get a y, and when you do it with a y, you ended up with a times x.
So if you had
Okay.
f is equal to 5 sine xy, the 5 would
Mhm.
still remain.
Yeah.
That's why the x still remains, right?
Let's try a version of that. Suppose I give you a function, and we'll put in a 5, and I'll change it to e to the power of xy, just to be a little bit different, right? If I asked you to find the partial derivative with respect to x, you would say, oh, chain rule, 5 is still there. E to the xy, right? That's that bit. And then wouldn't you differentiate the inside function? And with respect to x, can you see you get a y out of that guy? That makes sense? Are we cool?
Cool.
Right.
Yep.
Now, there are an unlimited number of things you can differentiate in Calc 1. Now that we're going to have typically at least 2 variables, can you see that there's like another dimension worth of things that you can now differentiate, but we have to be a little bit more careful about them. So here is a very innocuous looking question with a little bit of, you have to know how to find its derivative. It's not that horrible. I mean, it's just an x cubed on the top and a y squared on the bottom, right? It's not the worst looking equation in the world, but we're going to have to find its 2 partial derivatives, right? Now, the first one, let's find that one. And you have to look at this guy very carefully. Isn't y considered a constant? Right? So if I'm thinking about that, I'm thinking that is x cubed over 10. I'm just picking a random number, right? Isn't x cubed over 10 just like saying 1/10 of x cubed? The result is you multiply by the power, you reduce the power by 1, and doesn't the y squared really doesn't do much except stay out? Does that make sense? You see the location of y, right? Now, same guy, that fella. Put a little squiggly line here. If I'm going to differentiate this function with respect to y, I need to rewrite it like that. If I'd said to you differentiate 5 over x squared, wouldn't you call it 5x to the -2 so you could use the power rule? If I said to you 5 square root of x, wouldn't you call it 5x to the half so we can use the power rule, right? So I've got an x cubed over y squared. I want to differentiate with respect to y. I'm going to have to call it x cubed y to -2, right? That's equivalent. So now I can do the power rule, which is multiply by the power and then reduce the power by 1. You comfortable about that one? X cubed just like a number. It's like 5y to -2. Multiply by -2, reduce the power. And then style points. Not that there's much, but shouldn't you make it look like the original? Are we good here?
Yep.
Any questions? We're going to do as much practice as we have time for. Any more of these guys? Okay, let's try next fella. Do a fraction. Similar to 5. Suppose I do w equals e to the v over u squared plus v cubed. And we're going to find the partial derivative with respect to u. Would you agree that we have a fraction? That's pretty obvious, right? When you differentiate fractions, what method should come to mind? What technique do you typically do when you differentiate a fraction?
Quotient rule.
We use a quotient rule. Agreed. In this case, I'm going to stick to that rule. Top's going to be called f. The bottom's going to be called g. And the derivative is f dash g, take away f of g dashed, all over g squared. So far, so good. Now, each thing that I have to differentiate, I have to bear in mind that u is the only variable in time. So here's our first weird one. The top is e to the v, right? That's the top term. What is the derivative of e to the v with respect to the variable u? Big fat zero, John was showing. Agreed? V squared, still zero. Log of v, still zero. V to the 2 million, still zero. If you ain't got a u, all you are is a number, right? You're just a weird looking number. E to the v is just a weird looking constant. It's zero. So this guy is zero times that fella. Take away the top guy times the derivative of g. Now, with respect to u, that guy is simply just 2u. What about the plus v cubed? Will I get anything out of that guy? No, so I won't write plus 0, there's no point. And the bottom, squared. Now, 0 times anybody is 0, and multiply these two together. You're done. Quotient rule, partial derivatives, looking good. Now, there's obviously two versions of this. Let's see if something different happens when we do the other one. So the formula for calculating the derivative using the quotient rule is still that guy. Now, v is the variable. Okay. If you differentiate the top with respect to v, don't you get e to the v, right? It really is an answer. It's not 0. You leave the g alone. Take away, you leave the f alone, and you differentiate this guy, but with respect to v, so that's nothing plus 3v squared. I think my wife's trying to demolish the house. Oops, and I almost forgot. All over the bottom squared. Now, in a question like this, you should try the best you can to do some style points. The only thing I can see that's worthwhile is to pull out e to the v as a common factor. Are we good with that one? Quite different looking answers, right?
Yep.
But there is a theme here, isn't there? Everything else is just a number, and only one guy at a time is a variable, right? And it's still the same product quotient rules, just adapted to a multivariable situation. How are we doing? Are you ready? Do you want to see another one like this, or do you want me to move on to the next level up? Every level, things get trickier. What do you want? Shall we knock away the trainer wheels and jump right into pedaling that bike up a hill?
Might as well.
Okay, here goes. This one is a version of question 6. And it's AX. Actually, it's not a version of question 6. It is question 6. Because they all your question 6s are the same as that one, right? Most of the time, you know, powers change and things, but not this time. Now, what makes this one different? Have you noticed that there's now some more letters of the alphabet? A, B, C, and D, right? Not just your usual typical X's and Y's and numbers, but an A, a B, a C, and a D. Those 4 guys are constants all the time. right? There's a kind of rule in math that says if you use letters like A, B, C, they're always constants, right? They're never going to be treated as a variable, right? And if you use letters that are later in the alphabet, you know, like R, S, T, U, V, W, X, Y, Z, that kind of lettering, they are almost always going to be a variable, or at least at some point in its life, it's going to be treated like a variable. So I want you to think of that as 2, and that is 3, and that is 4, and that's 5, right? And treat it the way you would. So if I'm going to do a partial derivative, let's say with respect to x, it's a fraction. So isn't this just another quotient rule? Right? So it's going to be f dash g, take away f of g dashed, all over g squared. If you did, oh, okay, I'll put little brackets around it for emphasis, and I'll try and cover up the stuff that don't work. Right. What's the derivative of f with respect to x? Top row is f. What's the derivative of that top piece with respect to only x? Everything else is a number.
I think it's just
Yeah.
A.
Just a. Isn't by just 42 times 5 and it's still a number and numbers don't count, right? Because derivatives of them are 0. And isn't ax like 5x and you differentiate it, you get 5, right? Now you leave the g alone. Take away, you leave the top alone. And you differentiate g, which is the bottom guy. Now with respect to x, what's the bottom guy's derivative? What's the derivative of this with respect to x? Treat everybody else like a number.
C.
Just a c, agreed. And then you do cx plus dy all squared. And I would expect us to tidy this up. So I'm going to distribute the a. And distribute the c. Won't do anything really with the bottom except rewrite it. And won't that guy kill off that guy? You agree? ACX kills off another ACX. And the two terms that are left have a y as a common factor. So I'm going to pull out y as a common factor and leave AD, take away BC, and just rewrite the bottom untouched. There's your derivative with respect to x. Interesting thing about this function, technically isn't this every linear fraction in the universe? By a linear fraction, I mean a fraction where there's a linear term of x and y in the top and a linear combination of x and y's in the bottom, right? This function represents every single one of them. And this represents what the derivative with respect to x would be. Now, if you pick certain choices of numbers, isn't it possible to get AD take away BC to be equal to 0? Can you imagine I could pick an A, a B, a C, and a D, and that could happen? If I did that, won't this derivative be 0? Because if these guys are equal to 0, then the whole thing is 0. So evidently, if AD take away BC is 0, the function that you get has a 0 derivative. So what in heck is that telling us? Well, zero derivatives essentially mean that the slope's horizontal. And if it's horizontal all the time, it must mean that this fraction ends up being a horizontal plane. It's not obvious looking at that, what combinations of X and Y would generate it, but evidently that combination would do it. Now, I won't do the other one, but it's similar, right? Here's another one. This one, we're going to introduce some letters, another variable. We're going to have x squared plus 4y squared. And we'll finish with a takeaway 6z. And we're still finding partial derivatives. If you see the natural log of an expression and you want to differentiate it, shouldn't you be thinking general? Right, if I said to you, differentiate the log of x squared plus 1, shouldn't you be thinking general, right? So I want you to think of this whole thing here as our inside function. Now, if you differentiate this guy with respect to x, the derivative of a natural log gets you 1 over the thing. And then don't you finish with times the derivative of the inside function. And what's the derivative of this guy with respect to x? Two, 2x. And so you would end up with 2x over x squared plus 4y squared, take away 6z. Now, couldn't I, I'm not doing it, but couldn't I also find the partial derivative dw dy and the partial derivative dw dz? And it would look sort of like this one, but the top would be different each time. In fact, you could probably guess, if I did it with y, wouldn't the top be 8y? And if I did it with z, wouldn't the top just be -6? You could almost see it happening. Now, the next guy, I need to tell you a piece of information before we show you the question. And it comes from standard integrals. I'll do a number first. If I ask you for the derivative of 2 to the power of x, the answer isn't just 2 to the power of x. That's part of the answer, but it's not the whole answer. Does anybody know what the derivative of a base that's not e? Because if it was e to the x, it would be e to the x, and that's the finish.
From memory, I think it's
Yep.
going to be x natural log 2.
So again, John, didn't catch it.
Is it x natural log of 2?
Oh, not 100%, but 50%. Just natural log e 2 to the x. So you don't have an extra x, you just natural log e 2. So you're in the, definitely in the ballpark, right? So the derivative of 2 to the x is the natural log of 2 to the x. So the derivative of 10 to the power of x, which could happen, is the natural log of 10 to the power of x. And then if I generalize that and I say b to the power of x, where b could be 2, 10, or 20, as long as it's a number, right? So b has to be a number. Then its derivative is that guy. We're cool with that guy now? Now, let's do a partial derivative that incorporates this. And the one we're picking is going to be question similar to number 9. And we're going to have a function u, and it's 9x y to the power of z. So essentially this function has 3 variables, an x, a y, and a z. And we are going to do the partial derivative with respect to x. If you are doing this question and you're puzzling over, there's just too much happening here, it's hard for me to keep track what's going on. one strategy is leave the X, whatever that X is, alone, and take the other things, in this case, Y over Z, and let's just say, isn't Y over Z treated as a constant, right? It's treated as a number, right? Now, if I say it's the number 4, this guy, his derivative will behave very similar to this guy's derivative. Now, when you differentiate this guy, you would multiply by the power. So I'm not writing 36 down, I'm writing it as 9 times 4. And then you would reduce the power by 1, and I'm not going to write 3, I'm going to do that. Isn't that essentially the calculation that you would do to get 36x cubed, which is the answer, right? You'd multiply by the power, and then you'd reduce the power by 1, right? And what I've done here is I've taken this and I've imagined it with numbers, and that might help us figure out how this is going to work. Shouldn't you just multiply by the power and reduce it by 1? That's it all, right? So multiply by the power, which is actually that guy, and then reduce the power by 1, which is that guy. And so the answer is not very pretty, but that's the answer with respect to X. Does that make sense? I'm just multiplying by the number, the constant Y over Z, and then reducing that number by 1. You see, you need to have a kind of way to visualize and focus on one thing, in this case, X's, and then treat everything else like a number. That's the kind of trick to getting these done. Now, I'm just going to rewrite this guy again. We're going to do the next one. Now, this time, X is a number, and the Y is the variable, and the Z is a number. Right. Well, let's take care of the 9. Would you agree the 9's going to be there no matter what happens? So let's just forget about the 9. I've taken care of it. It's here. Now, if you wanted to look at this fella, X is a number, so let's make him 2. Y is a variable, and Z is a number, let's make it 3. Isn't this 2 to the power of something? Right. Now, if you want to differentiate this guy, you get that fella, you get a natural log of 2, and what else do you get because of the Y over 3? Because technically, isn't this also a chain rule? So what else do you get from here? If you differentiate Y over 3 with respect to Y, you get something, don't you?
1/3.
You get 1/3. Now, this is the equivalent with everybody except the Y being a number. Over here, then, I'll put it in red, you're going to get X to the Y over Z times the natural log of X times 1 over Z. Can you see that guy's like the log X, and isn't that guy like the 1 over Z? Now I'm going to make it slightly prettier. There's the second one. Now the one I'm not doing, because I'm really cruel, but you really do have to kind of work sometimes through the hard stuff. Isn't that the third one? The derivative with respect to Z. So start with this guy and differentiate with respect to Z now. A couple of clues. It'll be very similar to this one, right? But there is going to be a twist on the tail. See how that says Y over Z? Won't that be like 4 over Z? Which means you're going to have to differentiate 4 over Z. And that's a little bit trickier than that.
So that last one is 9 natural log x divided by z
Z
times x
to
the
the
power of
Y over
y
Z.
divided by z. Okay.
Yeah.
Wow.
I know, but that's basically the worst one in the set, right? Because there's one after that, or before that, it was a power roll or something, but that was easy. Okay, that is just that. The first derivatives. Now I'm going to move on to now finding second derivatives and then higher derivatives. And they, for the most part, aren't really anything extra. It's really just do what you've already figured out, but do it twice. So I'll give you an example of what's happening. If I gave you this function and I said, find its first derivative, you would do this guy. And then I would say, do the second derivative. And to get the second derivative, don't you just differentiate the first derivative? Right? And if I wanted the third derivative, which I don't, but if I did, wouldn't I differentiate this? And if I wanted the fourth derivative, I would differentiate the answer to this. And you could keep going till you get tired. We are going to look at second derivatives. So we'll start with a pretty straightforward one. Look where they start. 14, 18. Is that 13? Let's check them. Okay. So a version of this question is 13. And two of these second derivatives, I think, are going to be, I hope, pretty straightforward. So here's our function. And I want to find the second derivative. So the first derivative with respect to x is called that guy. And we're back to, I hope, the easy stuff. Multiply by the power, reduce the power by 1. Multiply by the power, reduce the power by 1. Are you comfortable with that one? Polynomials tend to be relatively straightforward. We're comfortable with the first derivative. Now, if I wanted the second derivative, the notation looks like that. So if you've seen fxx, do you realize they're saying just differentiate it, partial derivative, with respect to x twice? So you take this answer and power rule it again, multiply by the power, reduce the power by 1, multiply by the power, reduce the power by 1. Now I'm not doing this, but couldn't you do third derivative, fxxx, right? Couldn't you do it fourth derivative until you ran out of things, right? Until you got zeros probably. So this is called the second partial derivative. This is called the first partial derivative. And there's thirds and fourths and as many as you like after that. Now, let's do the first partial derivative with respect to y. So put a little box there, you see it? If you differentiate this guy with respect to y, you get x to 6. And this guy with respect to y, well, you multiply by the power and reduce the power by 1. And now you get the second derivative. Any volunteers? What would you get if you differentiated this term with respect to y? What do you get if you differentiate this guy with respect to y?
0.
Agreed. And this guy, you wouldn't write 0. And this guy, wouldn't you basically just get the negative ax to the 5, just like 10y gets you 10, right? And there's your second derivative. So far, so good. And then, just when you think you're comfortable, they do this to you. That also counts as a second derivative. And you notice it's got x and y in it. So let's interpret what that means. You read it in this order. You do x first, and then you do y second. So I already know that guy, because we found him. He's equal to this. So the next stage would be to find that guy. What do you think you do to this function to get that second derivative? What will we use as our variable to get this guy?
Why?
Why? Have you noticed then that there is no reason in mathematics why you cannot change from one derivative to the following derivative? You're allowed to change who you consider to be the variable. Right? There's no rule that says no, if you start with fx, you must be x's to the rest. No, you can mix and match any order you like. So here we're doing x first, and now we're going to do y. And if you do that guy, you get this fella. And this guy, you get 40 x to the 4y. I'm going to put a little circle around him. There is one last second derivative, and it's that one, right? We've done xx and we've done yy. They're quite different, which is not a surprise. We've now done this one. Let's do that one. Well, that means you start with f of y, right? You do this first and then that second. And this guy here is x to the 6, take away 8x to the 5y. And then you differentiate this with respect to x. Well, differentiate that as a power rule, multiply by the power, reduce it by 1, right? Differentiate this with respect to x, you multiply by the power, and you reduce it by 1. And that is him.
So what are you actually finding then? The slope of a plane or something?
Geometrically, I don't think it has a geometric meaning. I don't think it's a slope of anything. I think it's more an algebraic thing that you calculate. Strangely enough, when you get to Calc 4, that guy, or that one, because I'll tell you in a minute why it doesn't matter, you use this guy, and it tells you whether the answer is a local max, a hill, or a local min, a valley. So it actually allows you to tell the difference between a hill and a valley. But geometrically, I don't think it's a slope of anything, because you're cutting it this way, then you're changing your mind and cutting that totally different way. I think the only thing you'd get there would be a point floating in space, which really doesn't help much. Have you noticed that these two things are equal?
Are they always equal?
That's an interesting question. You're going to like the answer, Eric. As long as the original function, which is this function up here, as long as this function is continuous, and in the 3D world, continuous just means like a nice flowing hill, right? There's no funny, volcanoes shooting up to infinity, right? You don't get, you might see some of the shapes, right, in GeoBra where it curves up here and then it curves down there, right? Like there's rips in the thing, right? As long as it's just normal, smooth curve, this is always true. And I can't spell this guy. I think that's a spelling. French guy called Clairaut. And this guy Clairaut found out, one of the many things he found out was this guy. That those two second derivatives are always equal to each other, provided the original function is continuous. Now, if you turn it on its head, if they're not equal to each other, doesn't that mean the function's not continuous? And you can't always tell if a function's continuous or not, because even if you put it in GeoBra, it might look okay in the window that you've chosen. But couldn't 40 mile down the road there'd be a funny hill and a hole and the thing breaks apart and doesn't work, right? Couldn't it be discontinuous somewhere else? Well, Kilroe just says that as long as the functions are continuous, this is going to be true. And we will assume that this is true for all homework questions, which means is if you get a question where it asks you, as they do, to find the 4 second derivatives, won't you find that one, and that one, and just use this answer to fill in that one? So it'll save your work rate by 1/4. Cool? Now, while we're doing Clairaut's theorem, basically that's what that says, let me show you something else that Clairaut did. He expanded this property. Do you know how you can do third and fourth and fifth partial derivatives? If I went and asked you to find x, x, y, 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 right, for instance, that would be a fifth partial derivative. And can you see the order that you would work in, right? Clairaut's theorem says it doesn't matter what order you do those guys in, as long as there's 3 y's and 2 x's. So this answer will be the same as this answer, which will be the same as that answer, right? Now you might think, well, okay, it's a novelty. Why would that be even vaguely interesting? Imagine we have this function. Imagine we had, right, this function, and I wanted you to find that third derivative. Right? Now, if you did it in the order they said, wouldn't you be finding the derivative of this expression with respect to x? Do you really want to find the derivative of that guy with respect to x? Wouldn't it be much better to do a y first? And maybe, in fact, I'll put an x cubed there, and maybe you should do a y, and then an x, because wouldn't that revolve around a lot less work? So I would start with the derivative with respect to y, which would basically be this ugly thing. And that guy. And then I would do y again. But wait a minute, won't that just disappear as a big fat 0? And I didn't really need to work on it. And this is a power rule. And then I could do the x. So we should say thank you to Clairaut, because he has discovered that sometimes you don't do a derivative in the order that they ask you. Can you imagine there might be some situations where you change the order to make your life easier? Now, let's show you another thing that you can use to reduce your workload. And that is what's called symmetry. Here is an example of a function that is symmetric. A symmetric function is one that if you switch the x's and y's, right? So you turn all the x's into y's and turn all the y's into x's, you still get the function that you started with. So for instance, if I turn the x's and y's and switch places with them, wouldn't we get that? But if you think about that mathematically, isn't that the exact same as the guy you started with? Now, if a function is symmetric, which it is here, right, you can use the answer to that derivative to predict the answer to this. Now, I'm not going to do that one because it's too long, but can we pretend that the answer to this one was 2xy plus y over xy, right? Let's just say that's what the answer ended up being. If I wanted to use that answer to predict this one, because I know the function is symmetric, all you do is switch the x's and y's. So it would become 2yx plus an x over a yx. Sneaky. Now, can you imagine you do a second derivative? Let's just say, for argument's sake, that the second derivative ended up being this guy. Just for argument's sake. Then I should be able to predict what the second derivative with respect to y is, shouldn't we? If the function is symmetric, don't you just switch the x's and y's around? So you get 2y take away x, y squared, x squared. So if a function is symmetric, you can sometimes use this property to reduce your workload, because technically, don't you only need to find half the answers and you can always predict the other half. And by symmetry, switch the x's and y's around and you've got your other answer. Are we good? Any questions? So we've talked about finding second derivatives. Let's talk now about, we've kind of sort of touched on them, higher derivatives, right? 3 or 4. So I'm trying to find one in front of me. Let's do a fraction. So this is question 14. Okay, it's a fraction. We agree we're going to end up doing a quotient rule no matter which variable I'm trying to differentiate. So I'll call this F and I'll call this G. And we're going to be asked to find W of Z, Y, and X. Now, I can definitely do that in the order that they just told me. Couldn't I do that one first, this one second, and that one third? And it would work. I'd probably end up pulling my hair out. So I'm going to choose a different order. If you've got a fraction, as we do here, I think X before Y before Z would be a better order. Why is that likely to generate less work than this one? Well, if you look at this fraction, isn't it dead easy to differentiate it with respect to X? Because don't you just get 1 over that guy? You agree? Easier, less work. So, partial derivative with respect to X. Well, that's the only variable. This is basically a number. So you end up with 1 over Y plus 9Z. Now, if you do Y second, I could do that as a quotient rule. I could also rewrite it as a -1 power. And I think that's less work because I can do a chain rule on that. So it'll be multiplied by the power, reduce the power by 1, and then differentiate by the inside function with respect to Y, and the inside function with respect to Y here is just 1. And so we end up with -1 over Y plus 9Z squared. Then I can do Z. In fact, if I wanted to do Z, I should probably write it like that, do another chain rule. Multiply by the power, so it's positive. Reduce the power by 1. And finish with the derivative of the inside function with respect to Z, which is 9, And so we now have 18 over y plus 9z cubed. So there is the answer to that third derivative. Are we good? Now, suppose I asked you to do that one. Same function, that one. What would be a better order?
X to X, Y.
I agree. Now, if you do the partial derivative with respect to x, already talked about that one, you get this. If you do the next partial derivative with respect to x, something really weird happens and nice. What's the derivative of that guy with respect to x?
0.
0. And technically, it really doesn't matter, but for completeness sake, isn't the answer eventually just going to be 0 because the derivative of 0 is 0. So Clairaut does allow us to choose good order for derivatives. Now, if you didn't do it in the order that I said, but you did it in some other order, you will get the exact same answer, right? It's not like it won't work. Won't you just like double your workload kind of thing? And so being able to recognize the order in which you should do things is helpful for, to make your life simple. Now I want to finish this piece off with a rather annoying notation problem. Suppose I have, it doesn't really matter what the function is, very simple function. Suppose I've got this guy. That's the first partial derivative with respect to x, and it can also be written down like that. I don't have any problem, but you agree both those notations are pretty elegant. You know what you're being asked to do, right? Differentiate with respect to x. Okay. Now, if I asked you to do that, do you recognize it's a x first and then a y second? Because the notation says you read it like that. Great. When you use delta notation, this notation here, it's far clunkier. And the problem is that do you notice that the order of x and y is different? Now, I have no control over that notation. There are reasons why the second derivative with respect to x, then y is written like this and not back to front. It makes you feel a little bit better. Here goes. If you take this guy and you do a partial derivative with respect to y, do you see where the delta squared f is? And do you see that the way you write it, why the y comes before the x? That's essentially the reasoning behind why those second derivatives are written in that back to front, which is another reason why I prefer this notation. Isn't it much easier? Now, Clairaut gets us out of a hole. See, if you do it in the different order than it asks, aren't you still going to get the same right answer? But can you imagine they might give you a question where they tell you the order to do it in because it's the easiest order, right? They're trying to help you out. But you mix it up, right? And by that, I mean, they tell you in this notation and you mix it up and you think, oh, they want me to do y first and then x second. You could quite easily just add to your workload. It's not going to kill the question. It's going to be correct, but it's not very nice. Any questions? Basically, to get second and third derivatives, don't you just do what you do, but you do it twice or 3 times? one guy's a variable, the rest is a constant. Okay, let's show you something different. Right, you should be looking at question, where is question 15. Can I make that a little bit bigger? What you're looking at here in question 15 is a rather innocuous but very powerful equation called Laplace's equation. And the solution to a Laplace equation is any function u, a function of x and y, where the second partial derivative with respect to x plus the second partial derivative with respect to y, when you add them together, the answer is 0. And so you can imagine some questions, right, where that would be the case, right? You add second derivative of x, add the second derivative of y, you get 0. Laplace's equations are very useful because they are used in electronics, and they are used in heat flow, and they are used in wave functions. Essentially what they do here is that equations that solve that property tend to be very useful equations in modeling all sorts of weird things in the science world. So any equation that solves a Laplace equation could be a heat flow solution, could be a whatever it might be. Now, what you're looking at here is a whole bunch of functions. And some of these guys, more than one, is a solution to Laplace. In other words, this is true. So what you have to do is pick a function, check it out, and if the answer works, it's a Laplace, right? You put, let's suppose that one works, you check it, and let's suppose that one works, right? So you check the ones that work. Okay, there are 6 guys there. We're only going to do 2. Pick one. Don't matter if it's one that works or one that doesn't, it'll give us an idea of how to prove either. Who do you want?
Do the second one and the fifth one.
Okay, second one, I'll just write it down because it's going to disappear in a minute. That's me just writing it down. That's the second one, and the fifth one. Okay. So this question really gets you practice at finding second derivatives, right? That's what it's about. We are trying to see, does it solve Laplace's equation? In fact, we're saying, is that true? Well, let's take the first one, number 2. If you differentiate it with respect to x, the derivative of this guy is e to the negative x times -1, and the cosine y is still there. And if you differentiate this with respect to x, well, the derivative of a cosine is a negative sign, so you get plus this guy, sine x. Are we comfortable with that? With respect to x, you get this guy. With respect to x, you get this guy. If we then do the second derivative, with respect to x, this guy gets you another negative, so it becomes positive. This guy doesn't change. This guy becomes a cosine of x. Everybody good so far? Yeah. Is this function symmetric? If you change the x's and y's, would you get the same function that you started with? Any takers? Is this function symmetric? And I want you to pay special attention to that subtraction. And the answer is no. It's not symmetric. It would look almost perfect. In fact, if that was a plus, it would have been symmetric, which unfortunately means you have to do it the hard way. So differentiate this guy with respect to y. Well, a cosine gets you a negative sign, so you get negative x, e to the x, I should say, sine y. If you differentiate this with respect to y, that guy gets you positive and you get this fella. If you then do y a second time, a sine gets you cosine. Everything else stays put. And e to the negative y gets you a negative e to the negative y, and the other guy stays put. Now, that is the double x fella. That guy is the double y fella. If I take the answer to this one and I add the answer to that one, let's see what we get. Would you agree that this guy gets killed off by that one? And this guy gets killed off by that one. So the answer is 0. And that means it satisfies the Laplace equation. Now, the other one, this guy here. And I've just noticed something. Do you see that funny little h there? And that little funny h there? That's not a variable. It's not like the cosine of h times y. It's actually a function called the hyperbolic cosine. And the hyperbolic cosine function is very rarely used, but it does exist and it does pop up. And if you're interested in it, it's quite an interesting function. One of the uses for the hyperbolic cosine function is to solve this problem. Can you imagine that you had 2 points equal height and you had a piece of string that was longer than the distance joining them? If you just left those 2 pieces of string and attached them to the end, wouldn't it make a natural curve just because of gravity? Agreed? That curve uses the hyperbolic sine or hyperbolic cosine in its function. So probably the only people who are maybe going to use that on a regular basis, and I'm making this up, but it's probably true. Can you imagine people building bridges and they're doing the cantilever things? Can you imagine in those cases it might be useful to be able to model what the curve would look like so that when you're in the design stage of your bridge, you would know, I don't know what else you would want to know, but how many of these things going down you would want and what height they would have to be based on the length of the cable that you're going to be attaching to each of the posts. So back to the question. Well, if you differentiate this guy with respect to x, you'll get a cosine x and a hyperbolic cosine. And if you differentiate this guy, you get negative sine x and a hyperbolic function. And then if you do the second derivative, the cosine turns into a negative sine. And that guy's really treated as a constant. And this guy, you get a cosine. And that guy is treated as a constant. So even although you don't know what the hyperbolic cosine and sine are equal to, at least in this example, it really didn't matter. Wasn't it just a constant that get tagged on because both of them were using y? Now it gets a little bit trickier for the second one. If you differentiate this guy here with respect to y, you will get sine x times the derivative of the hyperbolic cosine. And I'm going to tell you what its answer is. It's a hyperbolic sine. And if you differentiate this guy, well, you still get cosine x, and the derivative of a hyperbolic sine is the hyperbolic cosine, which is not what you get when you do sine and cosine. Don't you get pluses and minuses? But the derivative of a hyperbolic sine is a hyperbolic cosine, and the derivative of a hyperbolic cosine is a hyperbolic sine. So there's no real change in the signs, which kind of makes differentiating them easy, right? Because you don't need to worry about pluses and minuses happening, right? They're always whatever they started life off as. Now, if I do the second one, this guy will be sine of x, which is our guy, and then you differentiate the scalar. And then you get a cosine x, and you differentiate this guy. And there is our second one. And now we're going to test if you add those two together, do you get 0 or not? Well, let's see. Would you agree that this bit gets killed off by him, and this bit gets killed off by him? So guess what? Yes, it is. Both the ones that you picked are solutions to Laplace. Both of them have the property that this is true. And just in case you think everybody is the same, here's one. Let's take that one because it's easy to do. That guy is 2x. That guy is 2. That guy is 2y. That guy is also 2. If you add those two second derivatives together, do you see that you get the answer 4? So that is not a solution to Laplace's equation, right? So there's one that isn't. How are we doing, guys? We're good. Okay. I want to do a few more of the higher derivative ones. Then I'll talk about evaluate, and then we'll finish on these implicits. So it don't really matter which one we pick. Right, let's pick a version of 16. So we have a function. And we're being asked to find that guy. So x first, y second, z third. Just superficially looking, would you agree that it probably doesn't matter which one you do first, second, or third? They're probably going to be equally ugly. So I'm going to do the order they said. If you differentiate this guy with respect to x, you're going to get e to the x, y, z to the 8 times the derivative of this fella. And with respect to x, you get that one. Are you comfortable with that? You know, e to the 5x gets you e to the 5x times 5. In this case, my 5 is just the y, z to the 8. Now it gets trickier. Let's do y now. When you look at this derivative, this function that we're going to find its derivative of, isn't there y's in both pieces? Now, doesn't that mean then that I should really do a product rule? And bear in mind y is the variable. So if you differentiate this guy here with respect to y, you get this guy, and you leave this one alone. Plus you leave this guy alone, and you differentiate this with respect to y. So you're going to get e to the x, y, z to the 8 times the derivative of this piece with respect to y, and that gets you x, z to the 8. So that's z to the 8, e to the x, y, z to the 8, plus that, and all the other stuff. So what's that? X, y, z to the 16, e to the x, y, z to the 8. I can pull out a z to the 8, and I can pull out an e to the x, y, z to the 8 as a common factor, and that leaves me with 1 plus x, y, z to the 8. This thing is growing like a monster, isn't it? It's just taking over the whole process. Essentially now, don't I have to differentiate this expression here? And I've just noticed that when I differentiate it with respect to z, don't I have 3 different pieces, all with z's in them? So I'm thinking to myself, do I really want to do a derivative with 3 pieces? And it is possible. And if you want to see the formula for it, it's f dashed gh plus f g dashed h plus f g h dashed. That would be an extension of the product rule to 3 variables. And if you did, you'd plug them all in here and get the answer. Or couldn't I just bite the bullet and do a product rule with this piece and a different product rule with that piece, and get the answer? I don't think there's any advantage to either method. They're just going to be ugly. And I'm just going to go ... and it's ridiculously ugly. And let me see if I can tell you the answer, at least for the one I've got, just to show you how bad it really looks. Is that 18? There it is. Can you see question 16? So what you're seeing on the screen?
Yep.
Yeah, that's the answer, right? At least it is for my combination. You're going to have a different answer unless you're fortunate enough to have an 8 up there. So we have one little and one major to do, and that's us pretty much covered. Let's do the little one first. Evaluating a derivative. So this is basically a version of the last question. We have y, the inverse sine of xy, and we're being asked to find the partial derivative with respect to y evaluated at 4,1/8. So we need to differentiate this guy with respect to y. That's f, that's g. I'm doing a product rule. And if that wasn't bad enough, you're going to see something worse in a minute. Differentiate that with respect to y, you get 1. Leave that guy alone. Plus, leave the first one alone and look at that guy. I want to differentiate an inverse sine function. And worse than just inverse sine, isn't it the inverse sine of xy? So it's technically a chain rule as well. Can anybody remember the derivative for the inverse sine of x? Just a simple x. Inverse sine of x.
I think it's 1 over square root of.
So far, so good.
Something over x squared, or
1 minus x squared. But in this case, we don't have an x, we have an xy squared, right? So that's the kind of adaptation, right? So it's 1 over the square root of 1 minus the thing squared, followed by, and the derivative of xy with respect to y gets you another x. So we are looking at the inverse sine of xy plus xy over 1 take away x squared y squared. So that's the differentiation part finished. Now we're going to plug in 4 for x and 1/8 for y. So let's see what that looks like. 4, 1/8. The inverse sine of 4 times 1/8, that's xy, plus 4 times 1/8, all over the square root of 1 take away 4 squared times 1/8 squared. That becomes the inverse sine of a half. This guy is a half. And this guy is 16 and 64, which is a quarter. And 1 take away a quarter is 3/4. And right now, that's what our answer looks like. And we want to make it pretty. If you go to your unit circle and you look for a y coordinate of a half, where would that be? About here. You'd find a guy that looks like that. So the inverse sine of a half is the angle whose y coordinate is a half, and that angle happens to be pi upon 3. So that's what the inverse sine of a half is. Now, how about this fella? I want to make him look pretty. Well, couldn't I call that the square root of 3 over the square root of 4, which is 2? I could then take this and think of it as the top guy divided by the bottom guy. I could then think of it as the top term multiplied by the reciprocal, and I get pi upon 3 plus 1 over root 3. And I said pi upon 3 then, I apologize, it's pi upon 6, but you can check it. My unit circle's off. The answer's here. And that angle there is pi upon 6. So you can find a partial derivative and you just plug in the value for x and y, and you make it look pretty by getting exact values. And that leads us to just one question. And there are 2 examples of this one question. And just see if I can find them now. And we're going to use a technique that we know how to use from Calc 1, and we're going to adapt it to this one. So the 2 questions are, I believe, 11 and 12, yes. This is 11. We have x squared plus 8y squared plus 7z squared equals 8. Now, in a nice world, this function would be written as z equals. And we would be asked to find, say, that guy. Or you might be asked to find that guy. That's a typical question. But it's not written as z equals. It's written in a combination of x's, y's, and z's. Yet we can still calculate, right, from this guy, we can still calculate what the partial derivative of this guy is. No, not do that one. By using what is called implicit differentiation. So the trick is to realize that x is the variable, which is obvious, and that z is a function of x. So you start with your original equation, and half of what I'm going to do I think is pretty straightforward, and the bit at the end is maybe not so. Differentiate this guy with respect to x, you get 2x. If you differentiate 8y squared with respect to x, I'm even writing it down, you get 0. If you differentiate 8 with respect to x, don't you also get 0? Now this guy here is the tricky part. When you did Calc 1, and I said to you differentiate 7y squared, wasn't the answer 14y dy by dx? Can you remember doing that? That was called implicit differentiation, right? So we are going to differentiate this guy with respect to x, but z isn't the same as y here. Z is considered to be its own function of x. And so you multiply by the power, reduce the power by 1, and then you finish with a dz by dx. In the same way that when you did Calc 1 and you differentiated y cubed, you would get that. Do you remember doing that same process back in Calc 1? I'm just repeating it here. Now what we do, not really doing anything here except making it look slightly pretty, is solve for dz by dx. So the first thing I'm going to do is subtract 2x from both sides, and then divide both sides by 14z. And if it's possible, make it look pretty. That is called, that process I've just done is implicit differentiation. Are you comfortable with the little trick at the end, which is this guy is treated differently than that guy? Right. And why do we know that? Z and X are both mentioned, right? So implicit differentiation, plus it tells you it's implicit. Now, if you do dz by dy, you'll get a similar result. So you should always keep the best till last. The last version of this, well, I mean, if that's like minor league, this is Super Bowl stuff. Here is the function that we're going to find the partial derivative with respect to x. It's got z's all over the place. That's fine. I'm going to differentiate this fella. You would get e to the 9z times the derivative of this guy, which is 9 dz by dx. So if you differentiate e to the 9z, you get e to the 9z times the derivative of 9z, implicit derivative, 9 1 times dz by dx, essentially. Now, on this side, I have an xy, and I have a z. X is also a variable, so I'm counting that as an f, and this is a g. So I now have to do a product rule to do a derivative of this guy with respect to x. This guy gets you y, that guy you leave alone. You have xy, and you differentiate this guy, and you get another dz by dx. So we are looking at that line. This stuff equals that stuff. I don't need the details here, but what do you think I'm now going to do for the next few lines? What do you think my goal is?
Separate.
Okay, so we got to figure out how you separate the dz by dx, right, from everything else. So what I'm going to do then is subtract this guy from both sides. Anybody any idea of what's going to happen to the left-hand side now? Nothing's going to change on the right now, but what do you think I might do to the left-hand side?
Factor out the DZ, DY. Or DX,
Okay.
excuse me.
Yeah, I know what you meant. That's this guy. And actually, we're pretty much finished. Because to complete the process, don't you just divide by that ugly guy? And that is the derivative with respect to x. Are we good?
Yes.
Right. It's a bit of a challenge here, but somebody might get it. I can make a prediction on the second answer. And the reason I can get away with that is this function is symmetric as far as x and y is concerned, and z. But x and y can switch places, which is an important thing. So you should be able to figure out what the answer looks like based on the fact that x and y are symmetric. Anybody want to have a guess at it? Use this to predict that.
You just replace a Y with an X and an X with a Y, right?
Yeah, so y with an x. Z's don't count, so change them, and y for an x, x for a y. Hey, wasn't symmetry nice to you? Because it means you get the second answer for free if you had to fight your way through the first answer. Or you just do it the way we just showed you and you'll get the same answer. Okay, any questions about what we've just done before we call it quits, and then I'll hang about for, you know, any questions you might have about the midterm or homework or whatever else.
So how do you know this is symmetrical again?
Oh, the original question, right? The thing we were differentiating is that guy. Now, the Z's don't count because both of them have the same Z, so they don't really matter. Can you see that the X and Y, if you switch places with them, right? If the only thing you did was switch places with the X and Y, wouldn't you get that? But if
Okay.
you rearrange that, isn't that the same guy you started with? So a function is considered symmetric if you switch the X's and Y's, you still get the same function that you started with after you've tidied it up.
Okay, cool. That makes sense. Thank you.
Right. Now, if that was squared and that was squared, it'd still be symmetric. But if that was a 12 and that was a 13, all bets are off. You'd have to do it from scratch because they are not symmetric anymore. These two guys don't matter because no matter what we do, aren't they still going to be the same two guys anyway? So they're not going to interfere with the symmetry. Okay. Any other questions? It's a good question. Well, you're still with me, so I'm glad that you hung into the end there. Bye-bye from now. I'll just hang about for, one-on-one questions that you may